This is example 8-2, where we're going to create dimensionless ratios based on a set of variables that we're given. For the first one, we're given length, time, and velocity. So let's see what their MLT dimensions are. So let's start with length. Well, it's easy. That's, of course, a length. Time, also pretty easy. It's a time. And then velocity is a length per time. Right? So we say length divided by time. So what does that tell us? Right? That tells us if we want to be dimensionless, then we'll have to multiply this velocity by time and divide it by a length. Right? So we can say, based on this, right, if we want to have dimensionless, we'd have to have the velocity, which is length per time. Now, if we want to get rid of time, right, then we have to multiply it by time, which then leaves us with a length, so we have to divide by length. And just to make sure, right, we'd have length per time times time divided by length. So that would be length time over length and time equal to 1. All right, so it's dimensionless just like we wanted to. Next, we have the surface tension, the bulk modulus, and a length. So same here, we'll write down what they are. So sigma has base units of mass per time squared. The bulk modulus, as we said before, is similar to pressure, so it would be m over LT squared. And then length is, of course, just length. And then we can do the same thing here. What does that mean? Well, if we look at these, sigma and the bulk modulus both have mass in them. So we probably want to divide those two by each other. So let's start with that. Let's say we're dividing the bulk modulus divided by sigma. Right? That means the masses all go away. The times cancel out, which is left. We're left with a length, so we'll have to multiply that by L. See how that works. So we said the bulk modulus was m over L t squared times L divided by the surface tension, mass over time squared. All right, so that would then be mass length times squared divided by length times squared and mass. So the mass cancels out, the L cancels out, so T's cancel out. We are dimensionless. All right, so again, we kind of have a look at what these units look like, and then we start making sure that they cancel out. The last one that we have is the velocity, the acceleration, the gravitational acceleration, and length. So we can say v is a length per time, velocity. We have the acceleration is g, that is length per time squared, right, meters per second squared, and then length is length. So what do we get? We have a time here and a squared times there. We don't have a time component here, so we'll actually have to have a velocity that's squared, right, to cancel that the t's can cancel. So we'd have velocity squared. G has to be on down here then to divide by it. That means now we have a length squared in front of a velocity term. That means we also need a length squared down here, but we only have one length, so we have to multiply that by L. Let's see if that works. So that would be length over time squared divided by length over time squared times length. So we would have length squared t squared, then we'd have a length, we'd have a t squared up there, and we have a length. Length squared and t squared equal to 1. All right, this was a quick practice on how to take a set of variables and make sure that that the ratio of them becomes dimensionless, because that's of course something that we need to do when we talk about the Buckingham pi theorem and in general dimensional analysis.